All right, folks, hopefully this works out. Um, I would like to introduce you to proofs. Before we get there, we got a little bit of journeying to do. Okay, so let's say we want to prove this idea. The sum of two even integers is always an even integer. The sum of two even integers is always an even integer. All right, the first step in doing a proof is to understand the statement. If you can't translate the statement precisely, you can't possibly prove it. So what words do we see in here that's interesting? You see the word sum. Do you remember off the top of your head what a sum is? Hopefully you think of that as the answer to an addition problem. If it had said product, that's the answer to multiplication, difference, subtraction, and quotient division. Okay, that's the first thing. Two even integers. Well, you better start with what's an integer. Do you know exactly precisely what the set of integers is? If you don't, you can't do the proof. All right, what's an integer? An integer is in the set ... -3, -2, -1, 0, 1, 2, 3. So it's kind of like all the counting numbers plus 0 plus all the negative counting numbers. There's an infinite number of objects, elements in this set. By the way, this funky looking Z with the double slash in the center, that is how we say in shorthand the set of all integers. So we can name an integer M. It's usually lowercase script. That is part of the set of integers. So you say M is an element of, this funky E means element. M is an element of the integers. We're identifying an integer, calling it M. We name things in proofs all the time. All right, now what else is an even integer? Well, you better identify what are the even numbers. So an even integer is any number in the set ... -6, -4, -2, 0, 2, 4, 6. Now here's probably how you haven't considered what an even integer is. It's any number that's divisible by 2 producing another integer, right? So a number divisible by 2 is how you might think about it. Let's say we name it the script letter lowercase a. That's arbitrary. We say that a is an even integer if a is equal to 2m, where m is an element of the integers. Let's think about this. Pick any integer in your head right now. Any integer. Got it? Okay, multiply that integer by 2. Got the new number? Awesome. Is it even or odd? It's even, right, and that'll always be the case. This is literally the definition of evenness. Take any integer, multiply it by 2, and you get an even integer. And in fact, you can generate the entire set of even integers that way. Okay, and then what's an odd integer? Well, I think we ... -5, -3, -1, 1, 3, 5. By definition, if we name an odd integer a, it's going to be a equals 2m plus 1. Makes sense, right? If 2m generates an even integer, then if you add 1 to an even integer, what kind of integer do you get? An odd integer. Again, pick any integer. Got something in your brain? Great. Multiply that number by 2. Got the new number. Add 1. Now tell me, is it even or odd? It's odd. Will always be that case. Here's your definition of oddness. I know it's new to you, but you need definitions and precision when dealing with proofs. All right, so we've got even integers, odd integers, sum products, difference. Now we should be able to interpret this entirely. The sum, that's an answer to an addition problem, of two even integers, two integers that meet the definition of a equals 2m, equals another even integer, another 2m kind of situation. All right, first step in doing proofs is precisely and definitively knowing every word in the proof. Next, before you even do the proof, you have to decide whether it's worth doing. If I told you that I am Santa Claus, you should not try to prove I'm Santa Claus because you'd be spinning your wheels. Because I'm not Santa Claus, right? I might have the beard, but that's about as close as I come. All right, I like to give gifts, but those two things are about as close as I come. The sum of two even integers is an even integer. Before you do the proofs, the deductive reasoning, you try to establish for yourself whether or not the statement is true by doing something called inductive reasoning. This is where you get a bunch of examples and see whether they all seem to work out. For example, two even integers. Maybe I pick the integers 2 and 4, and I take a sum of the two, and they come up with 6. Is 6 even? Yes. How about 4 plus 10? Two evens, you get 14, which is even. -6, -2, those are both even integers. You get -8, which is an even integer. 10 plus -12 gets you, actually -2, not 2. It should get you -2 here, which is also an even integer. So it seems like every time I pick two even integers and add them, I get an even integer. This seems like it's probably correct. Have I proven it's correct? No. I've proven 4 examples. There's literally an infinite number of examples here. So the only way to truly prove that this statement is true is to use a deductive proof, which somehow captures every case in existence. All right, so we move to deductive proofs, and we're going to do it in the following format, a 2-column proof. Here you go. The only way to learn proofs is to do them. Why? Because you've never seen them before. You're speaking a foreign language. You're doing it with more mathematical precision and reasoning than you've ever had to deal with in your life. If you're asking yourself why we're doing proofs in this class, well, it's a proofs class. It's the only one you do in high school. Why number theory proofs? Well, a number of reasons. It's going to make you smarter. Number 2, there's only 2 types of math that you find in Euclid's Elements, primarily geometry, secondly, number theory. Thirdly, if you just study geometry proofs, you'll never quite get what a proof is. You study at least 2 categories of math, let's say number theory and geometry, and we'll look at other ones too. You'll get a much better understanding of what you're doing when you're doing proofs. All right. So for the historical anachronism, for the growth in your brain, this is the best linear, precise thinking you'll ever do. So your brain is going to get stronger. You're going to make more neurological connections. You're going to be able to solve more difficult problems in the future. And it meets the historical requirements of this class. All right, let's take this through. First line. Remember, I'm trying to prove this thing at the bottom. The sum of 2 even integers is an even integer. How do we start? First thing we do is we name 2 integers. Why? Because the sum of 2 even integers. So we need 2 even integers to start with. We can't even start with the even integers. We have to start with integers. So name 2 of them. Okay, we'll call the first one m, the second one m. N. What's our reason? The reason is we're naming 2 integers. Sometimes your reason for your statement is just literally what you did. In this case, we named 2 integers. You're like, well, where'd you come up with those? How did you come up with those? Can you just do that? Yes. In proofs, naming is not sorcery. It is strategic. You're naming in proofs all the time. So we'll name 2 integers m and n. They're generalized integers. Now, we multiply those 2 integers each by the number 2. 2m and 2n, generating even integers. As we saw, that's literally the definition of even integers. So our reason is by the definition of even integers. So far, so good. Now we go back to naming. We have this even integer 2m. Let's nickname it a. We have the integer 2n. Let's nickname it b. Name the 2 even integers. Now you're saying, well, why do you keep naming things? Because it condenses things. It makes things shorter. It's much easier to say A and B than 2m and 2n. You may be like, well, really, is it that big of a deal? No, but as the proof gets bigger and bigger and bigger, yes. Naming will always make things tight, compact, and easy to cogitate upon. All right, now, what are we doing over here? It's not even an equation. It's just an expression, A plus B. I wonder why we did that. Oh, it's right here in the proof. If you had to underline some portion of what we're trying to prove here by A plus B, what would you say? The sum of 2 even integers, right? A and B are even integers, so this is the sum of 2 even integers. Add the 2 even integers. Again, the reason is just literally what we're doing. Next, A plus B equals 2m plus 2n. Well, how do we know that to be true? Because A equals 2m and B equals 2n. So just in place of A, put 2m. In place of B, put 2n. What do you call it when you take 2 things that are equivalent, you substitute one for the other? It's called substitutions. This is just substituting. For example, if I had, completely apart from this proof, if I had the numbers 3 plus 3, what could I put in place of 3 plus 3? 6. What else could I put in place of 3 plus 3? 2 times 3. Okay, no problem. Right? What else could I put in place of 3 plus 3? The square root of 36. Any of those could be substituted at will because they're all equivalent expressions. Whenever you substitute something in that's equivalent to something else that you know is equivalent, substitution is your reason. Okay. Now, what are we doing here? As you can see, we repeat the algebra. It's growing. It's just growing, right? We repeat the algebra. Here, we factored. Do you remember what factoring is? It's the opposite of multiplying. When you multiply, you take 2 factors, you multiply them, and you get a product. Okay, but sometimes, instead of doing that, you have some addends, things you're adding together, and you pull out a factor, turning the addition problem into a multiplication problem. Look at this right here. 2m plus 2n is an addition problem. If there's 2 addends, but if I factor out the 2, like kind of reverse multiplication here, factoring out a 2, now I have a multiplication problem. It's 2 times m plus n. There's 2 factors, 2 and m plus n. You see that? All right, so you can do multiply, you can factor. Why do you do one way or the other way? Depends what's useful to you mathematically. So factor. In all these proofs, you're going to factor in step 6. Well, what are we going to do next? We're going to say m plus n is an integer. You see right here it says 2 times m plus n. Well, it would be great if it just said like 2p, because then we'd know we have an even number. So what I want to do is deal with this thing right here, m plus n. It's an integer. How do you know it's an integer? Because integers are closed under addition. Now, you may never ever heard this term, closed under addition. What it means is this. Take an integer plus an integer, that's addition. You always produce another integer, only integers. You never say an integer plus an integer is a rhinoceros, or an integer plus an integer is Pee Wee Herman. It never happens, right? This is closed under addition. Integers are closed under addition means you always generate an integer when you add them. Multiplication is closed under addition. If you take 3 times 5, you get 15. Integer times an integer gets you an integer, not a donkey. It's kind of like, here's an analogy just to help you, okay? Humans are closed under reproductions, right? If you take a human male and a human female and they produce a human, right? They never produce some other kind or other species. So humans are closed under reproduction. In the same way, integers are closed under addition, multiplication, subtraction, not division, but under the first 3 they are. Okay, well, what are we going to do in step 8? The familiar concept of naming. M plus n's a lot to say, so let's nickname it P, name the integer. All right, we repeat the same algebra. See, in 4, then 5, then 6, now 9, expanded even further, right? Everything we're on line 6, and now in place of m plus n, we replace it with P. Why? Because P equals mn. That's what we named it. You're like, okay, well, why do we want to generate 2p? You'll see in a second, but we did is substitute 2 equivalent things. Now, 2p is an even integer. How do you know that? Because every even integer is an integer, p is an integer, times 2. That's how you generate an even integer by the definition of even integers. Now we nickname 2pq, name the even integer. Look how many times we've named. We named in line 1, line 3, line 8, now again in line 11. How many times do we substitute? We substitute in line 5, we substitute in line 9, we're going to substitute again in line 12. A lot of repeated reasons, right? Naming is not sorcery, it's strategic. Substitution is one of the most common things we do in all of mathematics, including in proofs. And a third idea here is a lot of the reasons will be repeated in proofs. So once you get familiar with the reasons, you kind of get familiar with using proofs. Anyway, now what are we going to do? Repeat the algebra. How many times have we done algebra? We started with the expression in 4. Then in 5, we did some substitution. In 6, we added some factoring in. In 9, we did some substitution. And here in 12, we do some more substitution. All right. Line 13, all we're doing is condensing the algebra. We went through the process of nicknaming to make this all easier to say. So now we can. Look, A plus B equals Q. Where'd you get that from? Right here. A plus B equals blah, 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 blah equals Q. So all we did was condense the algebra. A reason is what we're doing. And now finally, have we proven what we wanted to prove? Absolutely. We said A, right up here, we said A is an even integer. We said B is an even integer. We said Q is an even integer. So an even integer plus an even integer equals an even integer. Which even integers are these? Whichever ones they want you to be. This is why we're capturing literally every combination of even integers there is, every sum of even integers, and generating every positive even integer as a result of it. This is taking in every case, this direct proof is a proof with 100% certainty that this statement is true under every condition everywhere in the universe. All right, but how did we originally make the statement? We stated in verbal language, the sum of 2 even integers is an even integer. So we convert from this. What language is this? Geometry, algebra, or verbal? It's algebra. It's a variable with it's an equation with variables, right? So just convert it, just translate it into verbal. How do we write that? Verbalize the algebra. Make the algebra verbal. Okay. This is a 14 line, because there's 14 lines, 2-column proofs. 2-column proofs are a great way to express proofs. You have your statements, you have your reasons. And again, reasons are often just what you're doing. But sometimes it's an explanation of kind of the operation, like factoring or substituting. Okay. Lots of words there. Let's do another proof. When you have it, you might want to pause yourself. So just give yourself a break. Okay, now that you're back, let's go on to the next one. What are we proving here? The product of two odd integers is an odd integer. Let's go back a slide. No, we can't. Okay. The product of two odd. So product is the answer to a multiplication product. Odd integers follow the definition 2m plus 1. So they're like a is equal to 2m plus 1. Just to remind you of the truth of this statement. How do we know the statement's true? We can't know it for certain, but we can assume it's true based on examples. So let me choose two odd integers, 3 and 3. Let's multiply them. You get 9. That's odd. Okay, how about -5 and 1? We'll multiply them, you get -5, which is also odd. Let's take -3 times -7. Well, that's 21. 21 is also odd. Okay, induction, taking a bunch of examples, is telling me this statement's true, so it's worth proving with a deductive proof. Now, I want you to notice I structured all these proofs the same. All these number theory proofs that we're doing all look the same. 14 lines. You'll notice the reasons are virtually the same throughout, and the process is virtually the same throughout. Of course, you're multiplying using odd integers, so it's going to change a little bit, but you'll see how similar it is. First line, name those integers. M and N are integers. Name two integers. Not sorcery, strategic. In proofs, you name things. That's part of the process. All right, we're not interested in integers, but odd integers. So we multiply the m times 2 and add 1. 2n plus 1, and same thing. 2n plus 1 are odd integers. By the definition of odd integers, that's oddness for you. All right, let's name those long integers as a and b. Just set them equivalent. You're naming odd integers. Naming, very important. All right, a times b. A times b. That's how you write it, ab, right? Why? Because you're taking the product of two odd integers. Just take the beginning of this proof, right, as ab. Multiply two odd integers. All right, then you do some, what's this called? Substitution. Why? You're replacing a with 2m plus 1. A with 2m plus 1 and b with 2n plus 1. Can you do that? Yeah, they're equivalent. Whenever you substitute two equivalent things, called substitution. All right, keep the algebra going. Now, here's where you better know your basic algebra. Hopefully you know how to distribute. When you multiply a monomial times a monomial, easy. When you multiply a monomial times a binomial, you distribute. And when you multiply a binomial times a binomial, you must FOIL. First, outer, inner, last. Basic algebra. Maybe not easy for you if you don't remember, but it is basic, meaning elementary algebra, so you need to know it. How do you do first, outer, inner, last, or FOIL? You multiply 2m times 2n. That's the first, you get 4mn. Then the outer, 2m times 1, you get 2m. 1 times 2n, that's the inner, you get 2n, and then 1 times 1 is 1, that's the last. First, outer, inner, last, FOIL. Whenever you have two binomials. It's an add-in plus an add-in, that's a binomial, add-in plus an add-in, binomial. Multiplying binomials, you have FOIL. All right, so that's multiplying. FOIL is just a type of multiplying. Distributing is a type of multiplying, right? All right, now you're going to factor, just like you did in the last example, line 6, you factored. You're always going to factor here. What are you factoring out in the last example? 2. What are you factoring out here? 2. Like, why are we always factoring out a 2? So you either want to generate like 2p or 2p plus 1, either an even number or an odd number. So that's what you got to factor out. But you're only going to factor out the 2 from the first 3 terms here. You're like, why? Well, if you factored out a 2 from 1, you get a 1/2, which isn't going to help you get evenness or oddness. You either want 2p plus 1 or 2p. Here you can generate 2p plus 1, which is odd. All right, so just factor out the 2 from the first 3 terms. You're like, why? I don't get it. Well, watch this. Distribute if you're unsure. 2 times 2mn is 4mn. 2 times m is 2m. 2 times n is 2n. Do you see it? Hopefully you see it. Basic algebra, you need to know how to do it. All right. Now, what are we going to do? We're going to nickname this horrible thing 2mn plus m plus n. Well, first we're going to say that it's an integer. And then we're going to nickname it p. Why are we doing that? Because you're going to get 2p plus 1, which is odd. All right, you see what we're doing? 2m plus n plus m plus n is an integer. Why? Because integers are closed under multiplication and addition. 2 times m times n is multiplication. 2mn plus m plus n is addition. Look, if you add two integers, you get an integer. If you multiply two integers, you get an integer. Integers are closed under multiplication and addition. They never produce the Mona Lisa. When you add them together, it's always another integer. Okay. Closure, it's an important principle in real numbers. Well, in integers, it's an important principle here. Closure under addition, multiplication. All right, great. Then let's nickname this horror show 2m plus m plus n p. Why do you do that? You name things in proofs. Strategic, not sorcery. All right, then you bring back all this algebra from line 6. Line 9 is always bringing back all the algebra from line 6, and then you keep going. What are you going to do? Another substitution. You replace this thing with p. That's what it's called, p, right? So 2p plus 1. Well, 2p plus 1 is a what? It's an odd integer. By the definition of odd integer, can we nickname 2p plus 1 q? Yes, that's what we're going to do. Name the odd integer. Bring back all the algebra from line 9 and 12 and do some more substitution. 2p plus 1 is q. How do we know that? Because we nicknamed it q in the last line. Substitution. Like, why? Why do we keep nicknaming things? Why do we take the time to watch? Condense this algebra. AB equals q. AB equals q. Wow, that's easy to understand once you condense the algebra. A, we said was an odd integer. B, we said was an odd integer. What did we say q was? An odd integer. Well, therefore, an odd integer times an odd integer equals an odd integer. We proved what we were trying to prove. The product of two odd integers is an odd integer. See it? All right, now we just want to translate that from, what language is this? Algebra into verbal. Verbalize the algebra. Same 14 lines, same basic set of reasons. Now, if you look on the line, you'll see intro to proofs 1 and intro to proofs 2. I think there's 2 proofs that we had done in class for the first one, and then there's like 4 proofs in the second intro to proofs 2. And then in the first homework, you just had to reproduce the first 2 proofs because you'd never seen proofs before, so you're just reproducing them, just practicing reproducing them. In the second homework, you actually had 2 fresh proofs, which were variations on the earlier versions. If you look over the 6 proofs that I have done for you, and you reproduce the first 2, you should be able to do the last 2. Then you want to practice them, because these students, honor students, already had a quiz on this. I forget if I asked in your class them to the very first proof we did, or the second proof we did, but it was one of those 2 proofs. And you'll have another quiz on these proofs sometime probably in the first week you're back on all these number theory proofs. Okay, soon we're going to moving on to geometric proofs, which is out of chapter 2 in your book. But these number theory proofs, if you get them under your belt, going to be a huge help in giving you an understanding of what you're doing when you're doing direct proofs. It's a concept in math called duality. If you do math in one language and you do math in another language, or you do the same problem in the same language 2 different ways, your brain understands the abstract thought that you're really doing underlying languages, and you just grasp it more. And since proofs are brand new to you, they're a foreign language, you're going to just want to practice these. If you're super good at memorizing, which I gotta assume you are if you're 8th graders in 10th grade math, this will go pretty quickly. You'll see the pattern. If you're having any trouble with them, try to remember what you do in each line. Maybe get which lines you're naming in, which lines you're substituting in, which lines you're reproducing algebra in, that kind of thing. You'll get the pattern down, and then all the proofs pretty much follow it. At that point, your biggest challenge will be, do you know the basic algebra? Do you know the elementary algebra? Do you know to distribute? Do you know to FOIL? That kind of stuff. Or the factoring. If factoring trips you up, just remember you're always factoring out of 2. Either factor them out from all the terms or just the first 3 terms, depending on whether you're going even or odd. Beyond that, you'll find it quite repetitive. Sorry about that. I am on a different time zone than I started with. Sorry if I'm doing this in haste. It may not be the most high quality videos, but there it is. Hopefully it's helpful to you. I'm going to upload it now. Happy spring break.